Welcome to Understand the Math. In this Calculus 1 video, we're learning about the derivative as a function. We'll start by going over the formal definition of the derivative and then see how to use it to find the derivative of a function step by step. You'll learn how to graph a derivative from the original function's graph, see where a function is differentiable or not, and discover what higher derivatives tell us about how rates of change keep changing. Be sure to download the free guided notes to follow along and try the examples. Let's look at the definition of the derivative and walk through some example problems. The derivative of a function f of x is notated by f prime of x, and it's the limit of f of x plus h minus f of x, all divided by h, as h approaches 0. Let's now walk through some examples where we're going to find the derivative of the given function using the definition of the derivative. We're also going to state the domain of the function and then the domain of its derivative. I'm going to begin by writing down the formula for the derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now we're going to substitute in what f of x plus h is and what f of x is. Wherever we see an x, we're going to substitute in x plus h. So this is 5 times x plus h minus 4, and now we're going to subtract off f of x, which is 5x minus 4, and all of this is divided by h. Now all we have to do is just do a little bit of algebra. This is 5x plus 5h minus 4 minus 5x plus 4. Make sure that you carry this negative through to both this term and this term. And then all of this gets divided by h. Now let's see if we have anything that cancels. Our 5x cancels, and then our minus 4 cancels with 4. So this gives us the limit as h goes to 0 of 5h divided by h. And now you can see that the h's cancel, and we're left with a value of 5. So the derivative of our function is equal to 5. Now we're going to find the domain of f of x and the domain of f prime of x. I'm going to write this up here at the top. The domain of f of x is going to be minus infinity to infinity, because our function f of x over here on the left is just 5x minus 4. That is a polynomial, and a polynomial is continuous everywhere. Now let's talk about the domain of our derivative. Our derivative is equal to a constant 5, and that is continuous everywhere. So the domain of our derivative is also minus infinity to infinity. Let's now look at our second example. This is just a classic example to do when you're first learning about derivatives. We want to find f prime of x, so let's start with our formula. I think you'll find if you write the formula down each time you do a problem, you will begin to memorize it. We have f of x plus h minus f of x, all divided by h. This is the limit as h goes to 0. Wherever we have an x, we're going to substitute in x plus h, and this gives us the square root x plus h minus f of x, which is the square root of x, all divided by h. When we plug in that h goes to 0, we are going to get square root of x minus square root of x, which is 0, over 0. That is an indeterminate form. I have a video on evaluating limits with indeterminate forms like this if you need to review that. To evaluate this limit, notice that we have a square root minus another square root. That tells us that we should multiply by the conjugate. Let me write up here what the conjugate is. The conjugate of the square root of a minus the square root of b is the square root of a plus the square root of b. I'm going to go ahead and I'm going to erase the 0 over 0 just because we're going to run out of space if I don't. And now we're going to multiply by the conjugate. The conjugate is the square root of x plus h plus the square root of x. And we're also going to divide by that. And the reason that we have to do that is we can't change the limit. So we can only multiply by 1, which is what we just did. Now let's go ahead and let's use the FOIL method to solve this. I'm going to put parentheses around this top piece so it makes it easier. The FOIL method says the first thing we do is multiply the first terms, and that is the square root of x plus h times the square root of x plus h, so that just gives us x plus h. And now we're going to multiply the outer terms. So this is the square root of x plus h times square root of x. Now we multiply the inner terms, which is minus root x plus h. And then we multiply the last terms, which gives us a minus x, because that's square root of x times square root of x. And all of this is divided by h times the square root of x plus h plus root x. Now let's go ahead and let's see what cancels. We have an x that cancels, and then these terms with the square roots cancel, which is really nice. So let's see what we have left. This is the limit. As h goes to 0, we have an h on top, and then we have an h times the square root of x plus h plus root x. Now you can see that our h's cancel. And then we can go ahead and we can substitute that h is equal to 0. So this gives us an answer of 1 divided by 2 square root of x. And that's our answer. So the derivative of root x is 1 divided by 2 root x. We have one last thing to do, and that is to look at the domains. I'm going to do that over here on the left. So we can write down the domain of f of x. Now, whenever we have a square root, whatever is inside the square root has to be greater than or equal to 0. So our domain is going to be from 0 to infinity. Now let's look at the domain of our derivative. Our derivative is 1 divided by 2 times the square root of x. And because the square root of x is in the denominator, we know that x cannot be 0. So our domain is going to be an open bracket at 0 to infinity. We're now going to learn how to graph a derivative and walk through some examples. The derivative of a function f of x can be interpreted geometrically as the slope of the tangent line to the graph of f at the point x f of x. I have graphed the function y is equal to f of x. The slope of our function at x f of x is given by m subtangent, and it's the derivative of x at that point. So just remember, the slope of a function is the derivative of that function. Let's now walk through an example where we are going to use the graph of f to estimate the value of each derivative. In part A, we want to find the derivative at -1. So that means what we have to do is go over here to our graph find -1, and then find the slope at -1. That slope is equal to 0, so our derivative is equal to 0. Now let's look at part B. We want to find the derivative at x is equal to 0. Here's 0, and the derivative is going to be the slope of this line. Let me go ahead and let's write this in red so that you can see it easier. Remember that our slope is the change in y divided by the change in x, and from our graph, that looks like it's going to be -1. So our derivative is going to be approximately -1. Now let's look at part C. For part C, we want to find the derivative at 1. So let's go over here. There is x is 1, and then the derivative is going to be the slope right here. Let's go ahead and let's mark that in red. Remember that it is the change in y divided by the change in x. To see how much y changes, I'm going to go ahead and extend this line on up. So it looks like y is changing by a value of 4, while x changes by 1. So we are going to estimate that our slope is equal to 4, so our derivative is equal to 4. We're going to be looking at some examples where we're given the graph of a function f and asked to graph its derivative. To learn how to do this type of problem, let's look at some guidelines for graphing a derivative that's based on the original function's graph. Let's remember that the derivative is the slope of the function. If the slope of the function is 0, then the derivative is going to be 0 and cross the x-axis. If a function has a corner, that means the derivative does not exist, and you have to notate that by putting an open circle at that point. If the slope is greater than 0, the derivative is going to be positive and it's going to lie above the x-axis. Likewise, if the slope is negative, the derivative is going to be negative and lie below the x-axis. And then lastly, wherever you have the steepest slope, you are going to have the largest positive or negative value for the derivative. Let's first look at an example where we are given a function that's graphed in blue and a derivative that is graphed in red. We're going to use this example to learn how the graph of the derivative relates to the graph of the function. The easiest way to begin these types of problems is to first look at where the function has a slope of 0. Our function has a slope of 0 here and here. Whenever the slope of the function is 0, the derivative will be 0. And you can see that right here and right here, because the derivative is 0 there and crosses the x-axis. To the left of the first 0, the function f has a negative slope, and that means that the derivative is going to be negative and lie below the x-axis. The same thing happens to the right. Here the function also has a negative slope, and the derivative lies again below the x-axis. Now let's look at what's happening between those two 0 points. Our function is increasing or has a positive slope, so the derivative has to lie above the x-axis. To see where it lies above the x-axis, what you can do is look at the function and see where it is the steepest. Here it looks like the slope is the steepest right at the origin. And the slope of that line is about 3, so the derivative is equal to 3 at that point. The derivative then is going to start at 0, go up to this point, and then go back down to 0. Let's now look at the graph on the right. We're going to do something similar. We're going to start by seeing where the function has a slope of 0. Our function has a slope of 0 here, here, and here. And at those points, our derivative is going to be 0. So the derivative is going to be 0 here, here, and here. To the left of our first 0, our function is increasing and has a positive slope. So that means that our derivative has to lie above the x-axis. Our derivative then is decreasing and has a negative slope, and it looks like the slope is the steepest right here. So our derivative is going to be the smallest right here, and it's going to come down here and then go back up. And then on the right-hand side, our function is decreasing here. So our derivative lies below the x-axis. And then here, our function is increasing with a positive slope. So our derivative lies above the x-axis, reach a maximum here, and then comes back down. Let's now look at some examples where we are only given the function and we want to graph the derivative. We're going to first look at the graph on the left. Notice on that graph that we have no point where the slope is equal to 0, but we do have 2 points, one here and one here, where our function has what we call a corner, and that means that the derivative is not defined at that point. So our derivative, when x is -2 and x is 2, is going to have an open circle. Right now, we don't know where to put that open circle, so what we have to do next is look at the slope of each 3 of these pieces of our function. Let's look at this piece first. That piece has a slope of 1, so our graph is going to be equal to 1 up to this point, and there it's going to be undefined. Now let's look at our second piece. That graph has a slope of -1, so our derivative is going to be -1 between here and here, and at both of the ends, we are going to have an open circle. Let's look at the last piece. This piece has a slope of 1, and our derivative is going to be equal to 1 at that part, and we are going to have another open circle. Let's now look at the graph on the right. Let's start by looking at where our function has a slope of 0. That occurs right here. So our derivative is going to equal 0 at that point. When x is positive, our function is increasing, and it looks like it has the biggest slope about right here. So we can go up here and say it looks like our biggest value of our derivative is going to be about right here. And then notice over here on the right that our slope gets really close to 0. So our derivative is going to look like this. It's going to come up and then go back down. The same thing is going to happen on the left. Our slope has the biggest negative value at about this point, and that's about right here. So our graph is going to look like that. We're now going to learn how differentiability and continuity of a function are related and walk through some examples. There are 3 main facts about differentiability and continuity that we need to know. Here's the first one. If a function is not continuous at a point x is equal to a, then it is not differentiable at that point. I've put down here some examples of where a function is not continuous and hence not differentiable. Our first function is where we have a removable discontinuity at x is equal to a, And a function that has this type of removable discontinuity can look like this. F of x is g of x times x minus a over x minus a, where the x minus a's cancel out, and of course g of x is defined at x is equal to a. A function is also not continuous where it has a jump discontinuity, like at the point x is equal to a, and this function f of x is often a piecewise function where it's defined to be g of x when x is less than a and h of x when x is greater than or equal to a. The third type of an example where a function is not continuous is where it has what we call an infinite discontinuity. Here's an example of a function that has an infinite discontinuity and it has a vertical asymptote at x is equal to a. So in all three of these cases, removable, jump, and infinite, our function is not continuous at x is equal to a, and so it's not differentiable at x is equal to a. Here's our second fact. If a function is continuous at x is equal to a, it may or may not be differentiable at x is equal to a. So this basically tells us that continuity does not imply differentiability. Let's look at some examples of where a function is continuous but not differentiable. One of these cases is called a corner, and at this point, our function is not differentiable. This function is f of x is the absolute value of x minus a. The next type of function that is continuous but not differentiable is where we have what's called a vertical tangent. So at some point on a graph, the slope is infinite. An example of this type of function would be f of x is x minus a raised to the 1/3 power. The last type is where we have what we call a cusp. A function is not continuous and then not differentiable at the point where you have a cusp. An example of this is the function f of x is x minus a raised to the 2/3 power. The third fact is that if a function is differentiable at x is equal to a, then you can know that it is also continuous at x is equal to a. Whenever I teach this concept in class, I like to summarize these three facts in a chart. The first point is that if a function is not continuous because of a removable, jump, or infinite discontinuity, then it is not differentiable. The second part tells us if a function is continuous, it can be either differentiable or not differentiable. And if it's not differentiable, the function will have a corner, a vertical tangent, or a cusp. And then lastly, if a function is differentiable, it is continuous. Let's now look at an example where we are given the graph of a function f, and we want to state where the function f is not differentiable. Over here on the right, just as a reminder, I wrote down that a function will not be differentiable if it has a removable, jump, or infinite discontinuity, or if the function has a corner, a vertical tangent, or a cusp. Let's start looking at our x values as we go from left to right. When x is equal to -5, we have what looks like a cusp. So at x is -5, our function is not differentiable, and the reason is that we have a cusp. Let's now look at x is equal to -4. At that point, we have an infinite discontinuity, so our function is not continuous, and that means that our function is not differentiable. So let's write down x is equal to -4. We have an infinite discontinuity. Now let's look at the next point. That point is going to be -2, and at that point, we have a removable discontinuity. So our function is not continuous, and that means that our derivative is not continuous. So we'll write down x is equal to -2. We have a removable discontinuity. Now let's go over to where x is equal to 1. Here we have what's called a jump discontinuity. So our function is also not differentiable at x is equal to 1. And we'll write down jump discontinuity. And then we have one more point to look at, and that is where x is equal to 3. And notice on our graph that we have a vertical tangent at that point. So at x is equal to 3, our function is continuous, but the derivative is not differentiable. So we can say that we have a vertical tangent there. And that is why our function is not differentiable. Let's now learn about higher derivatives, in particular, how they're notated, what they can represent physically, and how their graphs are related. Higher derivatives of a function are just derivatives of derivatives. They tell you how a function's rates of change keep changing. A function is often notated as y or f of x. Its first derivative is going to be notated by y prime, or you might see it notated as f prime of x, or what we call df dx. A second derivative is notated as y double prime, or f double prime, or d squared f dx squared. And then lastly, a third derivative is notated by y triple prime, or f triple prime of x, or d cubed f dx cubed. A function can also represent the position of an object and be notated as s of t. Velocity is the instantaneous rate of change of position with respect to time and is notated typically as v of t or ds dt. This could also be written as s prime of t. Then we have acceleration, which is the instantaneous rate of change of velocity with respect to time. It's usually written as a of t or d squared s dt squared or v prime of t or dv dt. And then lastly, we have a term called jerk. It is the derivative of the acceleration function, and it is written as j of t or d cubed s dt cubed, or more commonly, just dA dt. Let's now look at an example where we have a figure that shows the graphs of f, f prime, and f double prime, but we're not told which one is which. Our job is to identify each curve. When I teach calculus, my students usually find this problem to be a little challenging, but we'll walk through it really carefully so you'll know exactly what to do. One good way to start a problem like this is to look at where each graph has a slope of 0. Our blue graph has a slope of 0 here, and then our red and green graphs also have a slope of 0 there. Because all these graphs have a slope of 0, that's not really going to help us identify which curve is which. Let's see where else these curves have a slope of 0. The red curve has a slope of 0 here, and then the green curve has a slope of 0 here and about here. Wherever a graph has a slope of 0, its derivative is going to be 0. Notice that there is a 0 right here that corresponds to our red graph having a slope of 0. This means that the green graph is the derivative of the red graph. Let's look again at the green graph. There is no 0 point here or here that corresponds to where the green graph has a slope of 0. So that means that the blue graph is not the derivative of the green graph. Let's now look back up at the blue graph. Notice that the blue graph has a positive slope all the time. That means its derivative has to always be above the x-axis. Notice that our red graph is always above the x-axis. So the red graph must be the derivative of the blue graph. We can now identify the curves. Our blue graph is going to be f. Our red graph is going to be f prime. And then our green graph is the derivative of the red graph, and it is f double prime. And that's it. You've learned how to find the derivative of a function using its definition, how to graph a derivative, how differentiability relates to continuity, and what higher derivatives represent. To really master these ideas, make sure you work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.